Okay, so take a look at this problem. First, give it a try and then we will discuss.
Okay.
So here assume that the system is released from rest. Okay, so whenever they give you such a system, so they assume that it is released from rest.
Yeah.
But in any case, acceleration should not depend on that. This is a fixed support, Abhiram.
Yeah.
The upper support is a fixed support.
Yeah. And I was running at a specific acceleration, and the car is accelerating. Is my acceleration plus the car's acceleration?
Yes, absolutely.
Okay.
So the accelerations, yeah, they add up, but you have to keep in mind that they add up vectorially. Okay, so
Okay.
not just like algebra. I hope you understand that.
Yeah.
Yeah, okay, good.
Direction as the positive direction. I'm
Okay,
saying that block A is moving at negative 6 meters per second squared
negative 6 meters per
acceleration.
second. So you have taken G as 10 here.
Yes.
Okay,
Yes.
okay. So negative 6. Okay, I don't know. So we will discuss and then
Yeah.
figure it out. Okay, and then
Okay. And then I got block B to be 3.5 meters per second squared down.
okay,
And then
okay.
block C to both be 8.5 meters per second squared down.
So that's also
Uh,
going
I, I,
down.
yeah, both are going down because A is going up, right? And so both of
Okay,
those will go down.
okay, okay. So, okay. So that means let us discuss and then see what we get. Okay. So let's hope those numbers are correct. Yeah.
Yeah.
Okay. Now, uh, what did you do? Matlab, sorry, Abhiram, you have to excuse me because my Hindi is bad, but still there are few uh, words which I routinely use. Okay,
Yeah.
so you might have heard me say "ठीक है." You might have heard me
Yeah.
saying "matlab." Okay, matlab is like means,
Yeah.
and TK is also TK is okay.
Yeah.
You might be familiar with Hindi, right? A little.
Yeah. The
Okay.
sayings I'm familiar with.
Okay. So let's talk about this. Now here, uh, so let's say, uh, okay. Oh, what is that? I'm not able to. Oh, okay. What did I do? What color am I using? This is a lot of learning in terms of using tools.
So online learning has been like a huge shift. Right?
Yeah, I think you would have seen from day one, I might have used several tools. Okay, so let me draw this again here.
Yeah.
This is A. B and C. Okay, so now if suppose if you consider that block A is moving up, okay, with acceleration, then the pulley will also move with the same acceleration but in the downward direction. I think that is okay.
Yeah. Yeah.
Okay. Now suppose, okay, so this A acceleration is relative to a ground person.
Yes.
Okay, so relative to a ground person. Now, if there is an observer standing on this movable pulley, so I always assume that there is an observer standing on the movable pulley. So this observer is a non-inertial observer. You understand this?
Yes.
So this guy is a non-inertial observer. Okay. Now, the accelerations of B and C are better first expressed in terms of what this observer sees. So, looking at the masses, I think C will go down with some acceleration, and then B will go up with some acceleration. So, I'm going to call them as A prime. Okay, so A prime is the acceleration relative to the non-inertial observer. Okay, or you can say it is relative to the pulley, movable pulley. Non-inertial observer or movable pulley. Are you with me so far?
Yes. Yes.
Okay. Now, that means I'm trying to analyze A with respect to a ground frame, but the blocks B and C are analyzed relative to a non-inertial frame. Okay. So the next thing that we need to do is we will have to get the free body diagrams. So if I think masses are 2, 3, and 5, right? Okay. So now if I look at the free body diagram of A, again, the same exercise. I think yesterday we were doing this. We took each object and then we started writing all the forces, relevant forces. Okay, so for A, we're going to take G as 10. So can you start telling me the forces that act on A?
Yes. So we have the gravitational force acting on the bottom.
Okay, so gravitational force, because the mass is 2, I think we're going to take it as 20
At
newtons.
the end,
Okay.
right?
Yeah.
Yeah.
What
And
other
then you
forces
have
are
the
acting?
tension force.
Okay, so tension. So there are 2 strings. So let's say this tension is T1. Okay.
I
And
think the
then,
question also asked for the tension forces.
yeah, it has. It has.
Yeah. So I got us out for those also. So.
Oh, okay, cool.
But,
We'll verify those. Okay.
yeah.
Because you got the accelerations, so I think the values of tension is just a byproduct. Okay.
Yeah.
Now here we are saying that block A is moving up with acceleration A. Now again, actually, if you are writing, let's say, a complete solution, the arrow T1 should better be slightly larger. Okay, you understand, because that is
Oh, yeah.
dominating, because the block A is moving up, right? Now, for I think we are done with the FBD of A. Yeah.
Yes. Yes.
So here, if I use Newton's second law, so net force is equal to mass into acceleration. So T1 upwards, I've taken positive here, minus 20 is equal to mass into acceleration, so 2 into A. So this is like first equation that we have. And then we will go to the free body diagram of B. Now you have to understand B and C are analyzed relative to the movable pulley or an observer moving with the pulley. Okay, so these are like with respect to non-inertial frame. You still remember the pseudo force concept?
Yes. Yes.
Okay, so we are supposed to use the pseudo force here, non-inertial observer. Okay. Now, can you tell me the forces that act on B? What forces
So
act on?
B is also there is gravitational force acting on B.
Okay, so the gravitational force, because the mass is 3 kg, the gravitational force is 30 newtons. Okay.
30. Yeah. And,
Yeah. What
there
other
is
forces?
there's a tension force acting on B from the pulley that it is on.
Okay, so that's totally a different tension. You understand that?
Yeah. Yeah. Yeah.
Okay,
Yeah.
so let's call that as T2. Okay, so that's in the upward direction. Yeah. Okay, so any other forces
And
that,
then
yeah, go ahead, Abhiram.
that should be it, right?
Remember, I was
Or
stressing on this
or
non-inertial observer point.
oh yeah. So the other tension force is also acting upon it, or
Oh, no, 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 no. That's not directly connected to that. Yeah, it is really. Well, it is going to be connected, but as
okay.
far as the
Yeah.
force
So
is considered, you remember how to apply pseudo force?
yeah. So if it's
See, pseudo force. I will write it here. Okay. So whenever you are applying a pseudo force is the magnitude is mass of the object being analyzed multiplied by acceleration of the frame. Okay. So here, what is the frame? If you go back to our discussion, what is that I'm trying to say here? This movable pulley, okay, I'm just assuming, I'm just imagining that there is an observer standing on the movable pulley. Okay, so that movable pulley is going down with acceleration A. Yeah.
so B should also be going down with that acceleration, right?
Fantastic. So B is definitely going down with that acceleration. So there are two ways. Okay, so if you don't want to use non-inertial frame, then you can actually get the acceleration relative to ground. Okay, so what is the acceleration of B relative to ground?
The acceleration of B relative to ground is that
In terms of A and A prime. Let's say if you're looking at those A and A
oh
primes.
it's A, that, oh
No.
it's A, it's it's going to be A1 minus A, right?
You mean A prime minus
Yeah,
A?
yeah, so A prime minus
Okay. Now let's look at it this way. Let's look at it this way. Imagine you have a very strong adhesive. Okay. So I think if you place an adhesive between the string and the surface of the movable pulley, so that means the string is like kind of fixed to the movable pulley. You understand? And
A. Yeah,
then B and C cannot really move relative to the pulley, right? So in that case, what is really happening? Uh, the movable pulley is going to go down with acceleration A.
yeah.
Okay, right?
Yes, yes.
But relative to the pulley, what is happening? B, because there is no adhesive placed. Okay, so uh, there's no adhesive placed. B is actually moving relative to the pulley. So that means B is also moving up. So I think you are right in terms of the magnitude. You said A prime minus A, or you can say A minus A prime. You get that?
Yeah,
But I think I'll give it to you because we don't know which one is greater anyway. Okay, so we can say that right now it is A minus A prime. So that is one way you can do. The other way is if I look at the one second, what is happening? Okay, so if I look at the pseudo force concept, okay, so the pseudo force idea is vectorially the pseudo force is opposite to the acceleration of the frame. Okay, now the movable pulley is our frame of reference.
yes.
It is going down with acceleration A. So then what do?
Yeah, yeah.
We actually apply a pseudo force in the opposite direction. So that means the pseudo force will get applied in the opposite direction. Now, what is the magnitude of this pseudo force? Mass of the object analyzed. So mass of the object is 3 and acceleration of the frame. So the frame acceleration is A. So 3A, you understand? So that's the pseudo
Yes.
force we're talking about. This is very, very important to understand. Now we know with respect to this non-inertial observer, there is this acceleration A prime in the upward direction. Okay, are you okay here?
Yeah.
So now if I use Newton's second law, okay, so the two forces that are in the upward direction are 3A plus T2, and the downward force is 30 newtons. That is equal to mass into acceleration. So 3 into A prime. But if you see this, Abhiram, if you see this, I could have written something like this. Okay, so I'm writing it here. T2 minus 30 is, you said it is like A prime minus A, right? So I could
Yeah.
have written it as A prime minus A. I'm assuming that you might have written like this, right? While solving the problem. Did you?
Yeah. Yeah.
Yeah. So if you compare them, there's no difference between them. Okay. So, but just that when you try to take the help of pseudo force in certain cases, things are slightly easier. Okay. Now, this is our second equation. All right. Okay. Now we'll have to go to the free body diagram. We're done with free body diagram of B. Now we'll have to look at free body diagram of C. Okay. So can you complete this is the free body diagram of B, FBD of B. Abhiram, can you complete the free body diagram of C? What forces
Yeah.
are,
So C,
yeah.
tension force and the gravitational force are acting on C.
Okay, so tension force is acting in the upward direction. So the gravitational force is
Gravitational force is 50 newtons.
50 newtons in the downward direction. Okay, so how about the pseudo force here?
The pseudo force will act in the downward direction for you, right?
No. What is the frame?
Oh,
Frame is the movable pulley. Okay, so the pulley is still going down with acceleration.
okay.
So on
So,
both blocks, B and C, the pseudo force is still in the upward direction.
okay.
Okay. So the pseudo force is still in the upward direction, but the magnitude differs because the mass of C is different. So mass
Yeah.
of C is 5 and the acceleration is A. You understand this step?
Yes.
Okay. Now we are saying that this is going down with acceleration A prime relative to the movable pulley. So now if I apply Newton's second law, I will write, okay, now I'm assuming that downward forces are dominating. So I'll have 50 minus 5A minus T2. This is equal to 5A prime. Are you okay so far?
Yeah.
Okay, now how many unknowns are there here? Abhiram, how many unknowns are there?
There are sorry, that is minus 30, right? In the second equation.
Yeah, minus 30. Yes, yes, that is 30.
Um,
So
there
how
are
many
four.
unknowns are there?
Sorry, three unknowns.
No, four unknowns,
Four,
right?
four
A
unknowns. Yeah,
prime,
sorry.
T1 and T2.
Yeah.
So we have only three equations. So we need one more equation. So how can I get the other equation?
The last equation.
Okay, so what we will do here is we will look at the free body diagram of the movable pulley. Free body diagram of movable pulley.
So the forces acting upon the movable pulley is
Okay.
gravitational forces acting upon it.
But what kind of
I mean,
pulleys are we dealing with?
on massless
Massless. So gravitational force I can ignore, right?
Yeah.
So that means there is tension force coming from above string, which is T1, and the other two strings, which are supporting blocks B and C, they are applying T2, right?
Yeah.
So even though the pulley is accelerating, because it has no mass, can I say the net force on the pulley is 0? Can I say
Uh,
that?
No, right? It doesn't have any mass. Right?
It does not have mass,
No,
right?
you can say. You can say.
You can say that,
Yeah.
right? See, mass is like really, really small, or we are ignoring it. Okay. So mass into
Yeah.
acceleration is almost zero. So the net force in the vertical direction is zero. So because net force is
Yeah.
zero, I can say that tension in the upward direction is equal to the sum of the tensions in the downward direction. So 2 times
Okay.
T2. So that is our fourth equation. You're okay?
Yeah.
So now you have these 4 equations to solve, right?
Yes.
Okay. So do you have these 4 equations with you?
Yeah. I wrote that down.
Okay. So I think let's start solving them. Okay. Now what I will do is, if you look at the what do I say here? I think can we eliminate maybe how should we do it? Okay. So T1 is 2T1, right? Okay,
Yeah.
so let us first eliminate, first add these two equations, 2 and 3. Okay, so adding 2 and 3, maybe I'll put all the equations together because we're not able to see everything, right? So let me put everything together.
Yeah.
Okay. So now let's see. Okay, so if I add 2 and 3, okay, so here if I add 2 and 3, okay, so what do I get? I think the tension disappears, T2 disappears. Okay, so I
Yeah.
have 50 minus 30, that is, I guess, 20 on one side, and then I'll have 20 minus 2a, right? So if I send 2a to the other side, I will check carefully. So I can write this as 2a plus 8a prime is equal to 20. Okay, so if I further simplify this, I can write this as a plus 4a prime as 10. Okay, so maybe we will call this as our fifth equation. You're
Yeah.
okay? Okay.
Yeah. Yeah.
Then we have this information that T1 is 2T2. Okay, so I can substitute that in the first equation. Okay, so if I
Yeah.
substitute that in the first equation, so here, so if I put it here, so this actually becomes 2T2 minus 20 is equal to 2A. Okay. Now,
Okay.
what I can do is I can take this third equation, I can multiply third equation by, so we have this equation here, right here.
Yeah.
I'm adding that equation to twice the third equation. You understand?
Okay.
So maybe I'll call this as
Yes.
sixth equation. Okay. I'm going to add equation 6 and twice of equation 3.
Yeah.
Okay. So when I do that, what do I get? That 2t will disappear. Okay. So I have minus 20 and then this 50 becomes 100. So that's minus 20 plus 100. So that is 80. And this becomes minus 10a. Okay. So the right hand side, I get this 2a and then this will be 10. This is 10a prime. So basically I'll have 2a plus
Yeah.
10a prime. Are you with me so far?
Yep.
Okay. So now maybe we should simplify this further. So we get 12a plus 10a prime is 80. So I think we can maybe simplify it further by dividing by 2. So I have 6a plus 5a prime is 40. Okay, so this is the other equation. So let's call this as seventh equation. Now we have two linear equations in variables a and a prime.
Yeah.
Okay, so now if I can solve these two equations, I'll get the accelerations.
Yeah.
Okay, so now what do I do here? If I look at fifth equation, there is just a. So maybe I will just multiply the fifth equation with 6a. Okay, so I'll 6a, and this becomes 24a prime. And the right hand side will be 60. Okay, all right. Now here, these two equations, from these two equations, I'm going to subtract. Okay, I'm going to, let's say, subtract seventh equation from this new altered equation. So I'm going to get what, 19a prime
Yeah.
is equal to 20. Yeah. So what is a prime? A prime happens to be 20 by 19 meter per second square. Yeah.
Yes. Yes.
Okay. Okay, now I can go back to, let's say, maybe fifth equation right here, and then get a. So I have a plus 4. A prime is 20 by 19, right?
Yeah.
I have, oh, what is this? Okay. So 20 by 19, and that is equal to 10. Okay. So now here, I think, what do we get here? This is 80 by 19. So I think it will be like 190 minus 80. So 190 minus 80 is like 110. 110 by 19 meter per second square. Are you okay so far?
Yes. Yes.
Okay. Now with these, if you go back, what are we saying here in this diagram? The acceleration of A, we got a positive number. Okay, so that means the acceleration of A, which is this 110 by 19 or under 19 meter per second square. So this is the acceleration of A. So we are done with acceleration of A. Now, if I look at acceleration of B, okay, so we said, okay, if you look at these, the pulley is going down with acceleration A.
Yeah.
Okay, and then a prime, a and a prime, which is greater? If you look at a and a prime, which is greater?
A is greater.
A is greater, right? So that means even b is going down. Can I write the acceleration of a will be a minus a prime?
Yeah.
Okay, so this would be, so a is 110 and this is 20. So I can write that as 90 by 19 meter per second square. Are you okay here?
Yeah.
Now, look at the acceleration of C. Acceleration of C is like the pulley is going down, so C is going down. With respect to pulley, also block C is going down. You understand that? So
Yeah.
the acceleration of C will be addition of these two vectors. So it will be A plus A
Yeah.
prime. So I end up having 130. Oh, sorry. 130 by 19 meter per second square. Okay, do you understand these values, Aviram?
Yeah.
Then, as far as the tensions are considered, if I use this first equation, which says T1 minus 20 is equal to 2A, I can use that to get T1. So T1 minus 20 is equal to 2A. So we got acceleration A as 110 by 11. So this would be 220 by 19. Okay, so Newtons. So T1 would be what? 20 plus 220 by 19. So how much is that? That's like 3. Can you add those? It's like 380. I think 600 by 19. Can you just check?
Yeah.
Yeah. So T1 is coming out to be this much, and then T2 is exactly half of this. So T2 would be 300 by 19 newtons.
Okay.
Okay. So do you get this problem? If you recall, let's say the previous class, we did one problem. I think in that problem, we didn't have 3 blocks. We had only 2 blocks. Okay, we figured out the relation between the acceleration of the blocks, and then we pretty much solved for the accelerations and the tensions. Okay, so I want you to revisit that problem and then see if you can actually simplify the solution here, because I know this is like too tedious, right? You have like 4 free body diagrams. Okay,
Yeah. Yeah.
and you have so many equations to solve. Okay,
Okay.
the tricky part is like you have to make sure that you are getting your free body diagram right, and then you are
Yeah.
applying the Newton second law carefully, and on top of that you also have to be super careful in terms of solving these equations, otherwise we will not get the answer. Okay,
Yeah. Yeah.
so now what I want you to do is spend some time, see if you can use the other approach, okay, which I taught you for that other problem. Use it for this problem, see if you can simplify the solution. I'll give you maybe around 5 minutes.
So
Yeah,
bring
is
up
it all
the
right?
other. Yeah. And then the other. Just assume that it was like a 8 kg weight.
Okay.
Try to find the
Okay, no,
acceleration
no,
and
no, no. You
tension.
should not do that
Yeah.
because B and C are actually moving uh, relative to the pulley. In that case, you will actually not get the accelerations of the blocks B and C. You will actually get the acceleration of the center of mass of B and C. You understand? So if you take them together, you're going to get the acceleration of the center of mass of B and C. Okay.
It's wrong to take
Yes, yes.
A and the other pulley as a as
Yes.
like one.
Yes, because what we want is we want the accelerations of B and C separately. We don't want the acceleration of the center of mass of B and C. Okay, so if you were actually looking at the acceleration of the center of mass of B and C, yeah, you could do that. Okay, because they're moving sort of not alike, right? Okay, so B, if you look from the
Yeah.
ground, B is actually in fact going, let's say, downwards. C is also going downwards, but they're actually going at a different rates. You understand? Okay, so both B and C are going downwards, but they're going at a different rate, different accelerations.
Okay.
Okay. So again, you're able to see the board?
Yes.
Okay. So we are again looking at the same system here.
Okay.
Now let's understand this, okay? Aviram, if I draw a line here, let's say if I take a line here. Okay, so this line is fixed in space, kind of it is stationary.
Yeah. Yeah.
Yeah. So if there is any observer at this level, okay, so if you have an observer at this level, I can say that this is a stationary observer, or often we say ground observers.
Okay.
Okay, so here the method that we are using is, okay, Okay, so you understand what I said? So this guy is kind of a stationary observer. Okay.
Yeah.
Now, we're going to say that this guy takes a sign convention that anything that is pointing in the downward direction is positive. Okay, so anything pointing in the downward direction is positive. So from this reference line, okay, so this is our reference line. We're going to write the positions of these blocks. Okay, so I'll say this is position of block A. Okay, and this pulley is moving. Okay, so we try and write and say that this is position of the pulley here, and then from here I can also say that this is the position of block B. Okay, and then this is position of block C. So the person is measuring these positions. You understand this? Yeah, Abhiram?
Yeah.
Okay, now we have two strings here. Okay, so I have colored coded them. So I have a white string and then a yellow string. Okay, now I can actually express the length of the string in terms of these positions. Do you understand what I'm saying here? Okay, I'm going to express the length of the string in terms of the positions of the blocks and the pulley. Now, to do that, we need a little additional information, which may not be relevant, but we need. Okay, so if you take this pulley, we are assuming that it is circular, and the radius of the upper pulley is, let's say, I'll take it as R1, and the radius of the lower pulley is R2. Okay. Now, with this information, I'm going to write the length of the upper string. Okay, Abhiram, for the upper string, okay, so length of upper string. Okay, so let's say I call that as L1. What is the length of the upper string? I'm going to take YA. Okay, so pay attention here, YA, and you have this portion of the string on top of the pulley. So that's like assuming it is circular, it is like pi R1, and then this string that reaches the movable pulley. So YP. Are you okay here?
Yeah.
So I'm writing the length of the string in terms of, sorry, the length of the string in terms of the positions. Yeah, right. Then I'm going to do the same thing for the lower string. So the length of lower string. Okay, this one note gives trouble. Okay, so that will be L2. So now how do I get that? If you pay close attention here, I need this much, right? So this chunk, this portion, okay, this portion. So that is obtained by subtracting YP from YB. You see that? YB from YB, I subtract YP. So if I do that, I will get this portion of the string. Are you with me?
Yeah.
And then I get this portion on top of the pulley, which is pi R2. And then this portion. So how do I get that? That is again YC minus YP. Are you okay so far?
Yeah.
So the length of the second string, the lower string, I can express it as YB plus YC minus 2YP plus pi R2. Now, from these two equations, okay, so I am not interested in the position of the movable pulley. You get that? So what I'm going to do is I'm going to add twice of L1 to L2. So if I add twice of L1 to L2, that YP disappears. So I end up having 2Y1, YA, I have YB plus YC, and then I'm going to write the other constant. So I have 2 pi R1 plus pi R2. You're okay so far?
Yeah.
Okay, now at this point, what we realize is, can you identify the constant terms here? Abhiram, can you identify the constant terms and the changing terms, the varying terms?
Yeah.
Okay, what are the?
The constant terms will be the length of the string is a constant term.
Very nice. The length of the string is constant. So a combination of the length will also be constant. So can I say this whole combination is constant?
Yeah.
Very nice. Anything else that is constant?
The radius will always be constant of the.
Fantastic. So radius is constant. So this combination is also constant. Very nice.
Yeah. But everything else will change, like YA by B.
Yes, everything else will change. Okay. So now here, if we use like a little bit calculus, so we are saying that we are taking time derivatives. Okay. So taking time derivatives here, taking time, oh, this one note. Okay. So taking time derivatives. The left-hand side is a constant. So when I take a derivative, I get 0. Now, what is the rate of change of position? Rate of change of position is velocity, right?
Yeah.
So I'm going to get this as 2VA plus VB plus VC. All right. And then if I take derivative once more, I'll get 0 is equal to twice the acceleration of A plus the acceleration of B plus the acceleration of C. Now, these are called constraint relations. Okay.
Okay.
Okay, so these are called constraint relations. Now, once we have these, okay, so these are nice, but yeah, since you're doing it for the first time, I think you have to be careful here. But otherwise, let's say when you do such a problem for the next time, you realize that I don't really have to worry about the portion of the, let's say, string over the pulley. So you can actually ignore that and then directly arrive at this equation. Okay, so the last equation, in fact, you can arrive at rather quickly. Are you okay?
Okay. Yeah.
So then next, what we want to do is, again, there is no running away from the free body diagrams. Okay, so this is just something known as a constraint analysis, which is connecting the acceleration of the blocks with a single equation. But we cannot go away with the free body diagrams. Okay, and here the free body diagrams we are showing relative to the ground observer. Okay, and then the assumption is anything pointing in the downward direction, vectors pointing in the downward direction is positive. So let's say if I take a look at A, okay, so if I take a look at A, I'm assuming that A is going down with acceleration A. Okay. And what are the forces acting? 20 newtons in the downward direction.
Yeah.
And in this case, what I will do is the tension in this string is T, suppose. We understand that the tension in the upper string will be 2T. You get this?
Yeah. Yeah.
Okay, so I can show directly 2T here. So here, because I have assumed that downward direction is positive, so what I can write straight away here is one equation is 20 minus 2T is mass into acceleration. Mass is 2, so 2A1. So we get this equation. Okay, so from here you get acceleration of A as 10 minus t. So which we're going to use it. Okay, so we're going to use that. Now similarly, if I take a look at the free body diagram of B. Okay, so if I take a look at the free body diagram of B, even B is assumed to go down with acceleration AB. So what forces are acting on this? B has a mass of 3 kg, so 30 newtons is acting downwards, and then tension T upwards. So here we write 30 minus T is mass into acceleration, so which is 3 AB. So from here I can write AB as 10 minus T by 3. Are you okay so far? So we have AA and then you have AB. Now let us look at the free body diagram of C.
Yeah.
So here the free body diagrams are rather simple because we don't have to worry about relative acceleration. Everything is assumed to be worked relative to a ground frame. Okay. So here the gravitational force is 50 newtons. Tension is T here. And then we said we are assuming that it is going down with acceleration AC. And again here. So like we wrote for B, we can say 50 in the downward direction, tension in the upward direction. That is equal to mass into acceleration. So which is 5 into AC. So what is, AC. So what is AC here? AC is 10 minus T by 5. Now you take these equations, okay, so I have AB, AC, and then AA, and then substitute in our constraint equation, okay. So if you substitute in our constraint equation, what I think we have 2A actually directly. So 20 minus 2T I will substitute here. I get 20, oh, okay, so 20, okay, 20 minus 2T. Okay. And then what is AB? AB is 10 minus T by 3. So I'm going to substitute that. 10 minus T by 3. Okay. And then AC is AC is 10 minus T by 5. You understand this substitution? So here the idea is, the big idea is we're going to get tension from here directly. So I have 20, 10, 10. So that's 40. And then if I add these two, what do I get here? I get 2T, and then I think the LCM is 15 here. I think you can handle this, right, Abhiram? So that's 30, 35, and I think 38 by 15.
Yeah.
I'm okay there?
Yes, yes.
Okay, so from here, the tension comes out to be, I think that's like, if I divide by 20, sorry, 20 into 15. So how much is 20 into 15? That's 300, right? So we get 300 by 19 newtons. Did we get the same answer for the tension in the lower string with the other approach?
Yes, we got the same answer.
Yeah. So the upper string will have 600 by 19. Okay. Then what we do here is, with our first approach, we obtained the accelerations first and then the tensions. With this approach, the constraint relation approach, we get the tension first, and then we go back to the equations to get the acceleration. So if I take a look at this, okay, so let me, okay, so AA is 10 minus T. Okay, so acceleration of A is 10 minus T. So 10 minus t will be 10 minus 300 by 19.
Yeah.
So that's a negative of 110. What is this negative signifying here? Abhiram, can you tell why are we getting negative here?
Negative just means the opposite direction, like as opposed to
Fantastic.
down is going up.
Very nice. So we have assumed that they're going to move downwards because we have a negative number. That means they, in fact, in reality, they will go upwards. So they accelerate upwards. Very nice. So similarly, I can get
Yeah.
AB, acceleration of B, as 10 minus t by 3. So, okay, so if I divide by
Yeah.
3, I think that is 10 minus 100 by 19. Okay, so we end up having 90 by 19. I think we got the same
Yeah.
answers, right? 90 by, but I think we got everything moving downwards, right? Here it is not matching.
Yeah. Yeah.
So what is happening here? Here, since we are getting positive, so that means B is actually accelerating in the downward direction. I think that is okay.
Going.
Yeah. I think we got B going down only.
Yeah.
Yeah. We
Yeah.
are fine. So AC
Okay.
is 10 minus, we'll verify this. So T by 5, so that is 10 minus, if I divide by 5, I think that's 60 by 19. So we got around like 130 by 19. So let's verify and then see if these are the answers that we have. Let's go back.
Those were.
Yeah. So AC is 130 by 19 and then AB is 90 by 19.
Yeah.
Yeah.
90 by 90.
Okay. So you understand. I know I've taken only one problem for such a long time, but this is a good problem and you understand.
Yeah, it was good. Yeah.
Yeah.
It went through all of the topics that I need to know.
Yes. So there's like you will have an opportunity to correctly write the free body diagrams, appreciate the constraint analysis, and then you need to be courageous enough to solve those equations. Okay.
Okay.
They're easy. They're simple equations. Just too many floating around. That's it.
Yeah.
Yeah. Okay. Yeah. So take a look at this problem. Abhiram, each block has mass m.
Okay. Yeah. All of them are weigh the same. Have the same. Okay.
Yes. Be careful here. There is friction between the blocks B and C and the horizontal ground.
Yeah.
That kinetic friction is given.
Okay. Yeah. That be weightless and the strings are all massless and cannot stretch.
Yes.
Okay.
The strings cannot stretch. Yes.
Okay. We have. I've written obviously gravity is acting upon A.
Okay.
Force mg.
Okay.
And then tension force is acting up, and tension force is pulling up on A.
Okay. Yeah.
Right.
Yes.
Yeah, and that should be it, correct?
Very good. So that should be it. Yeah. And then how about B?
And then block B.
Yeah.
You have to the right of block B. You have the can we call the tension force pulling up on a tension or?
Yeah, you give it some name. Maybe T1. Yeah, T1.
Yeah.
Or
Okay.
like something.
We can call it T1. Then. Okay. I think originally I wrote that B to the right. There's a force T1 pulling on B, but I'm thinking that's incorrect because they should not have the same.
Why do you say so? You mean to say?
That, but now I'm thinking no, because
you mean
like
to say
the tension forces of
right here and then
the
here?
Same, right?
Okay.
Yeah,
okay.
Yeah.
Between B and C and A and B. Yeah, you're right. They're two different strings.
No, I meant
Okay.
To the right of B and to the up of A, are those also equal?
Okay, so
Because
why do you think they're not equal?
it doesn't, they shouldn't be equal, right?
Okay, so let
Because A
me,
is also having to, like, the tension force of A should also include C,
okay, so let me
right?
throw you an argument here. Okay,
Maybe.
so
Yeah.
suppose, okay, so suppose, what is happening here? Okay, suppose if I take, okay, so if I take maybe any portion of the string connecting A and B. So whether I have taken a horizontal section. Oh, 1 second. I think I'm still in the shapes mode. Okay, so Abhiram, pay attention here. So let's say, suppose if I pick a vertical
Yeah.
section of the string. Okay, so if I pick a vertical section and I'm picking a horizontal section. Okay. Now these sections
Yeah.
are massless, right? You understand?
Yes.
These sections are massless. Okay. So now, if this is the section, let's say from here I have pulled this, and then from here I have pulled this section. Okay. Now,
Yeah.
the force in the downward direction, if I call it as T1, the force coming from the upward direction as T2, the entire string is massless. So that means if I take any portion of the string that is massless, you get my point, Abhiram? Abhiram, you understand the any portion of the string
Yeah.
is massless.
Okay.
So that means the
Yeah.
force in the upward direction is equal to downward direction. So T1 is equal to T2, right? And then the horizontal string, I can argue in the similar tone that let's say I have some force to the left. Let's say I'll call that as T3 and then force to the right, T4. So these are equal. Okay. Now you look at this. Okay. So if I start doing that by section, Abhiram, so if I start taking section by section, what is going to happen? Every time I'm going to say, if I pick a section, the tension at point at the upper
Up
section
and tension below are equal.
are equal. So you continuously do that, right? So that means whatever tension you have here, so they will end up being equal. You can
Okay.
continue
So
this logic.
okay, I was correct in the
Yes,
assumption. Okay.
you're
Yeah.
yeah,
So
you
then
are correct if you have taken them as same.
okay.
Okay.
So to the right of B, if in the free body diagram, if I say there's a force T1
Yeah.
pulling on B,
Yeah.
that's okay.
Yes,
And then
that is okay.
obviously gravity and normal force are acting upon this block B,
Yeah. Yes.
which cancel out,
Okay. Yeah. Correct.
and then there's tension T2 acting to the left of B.
Fantastic. Good. Yeah.
Uh, the frictional force mu k into Fn, right?
Mu k
Fn
into
being
no mu k into normal
normal
force.
force.
Yeah. Mu k into normal force
Yeah,
is going to act in which direction?
opposite to the tension 1,
Very good. Very good.
to
Yes.
the left of B. And
Fantastic.
then
So yeah.
we have we have to the right of C T2 is
Yeah.
acting on the right of C.
Yes. You're right.
Force. And for block C also you have the friction force mu k into normal force.
Perfect. Perfect. I think you're absolutely correct when it comes to the free body diagrams. Now you just have to use Newton's second law, write the equations, and then solve and then get the answers. Okay, so I'll give you a few minutes then.
Yeah.
Yeah. Okay. Good. Good job. Abhiram, I think I lost you. Abhiram, I lost you
Oh,
actually. So we'll do one thing, okay? So because you have your free body diagram correct, uh, I am very hopeful that your answer will be correct. Okay. So what we will do is we'll verify and then see what we get here. So I think this is the free body diagram I have just drawn. Okay. So that is okay for these three blocks. All right, Abhiram?
yeah.
Okay. So now, because
Yeah.
A has acceleration A in the downward direction, both B and C, because they're all connected, so they should have the same magnitude of acceleration. So B and C are moving with acceleration A to the right. Now, if I apply Newton's second law for A, the gravitational force is assumed to be dominating. So mg minus tension is equal to mass into acceleration. All right. Now this is for A. Now for
Yeah.
B, T1, I'm calling this as T2. Okay, so T1 minus T2 minus the friction force acting on B should be equal to mass into acceleration, which is ma. Now here, if I write down the frictional force is mu k times normal. And then from here, clearly normal is mg. So you might have written mu k into mg. Is it okay, Abhiram?
Yeah.
Okay, so that is for B. Now for C, I have T2 minus Fkc, the friction acting on C is equal to mass into acceleration. So this would be T2 minus mu k mg is equal to mass into acceleration. Now what can we do here? If I add these three equations, can you see T1 and T2 cancelling?
Yeah.
Okay, so if I add all of them, I can write mg minus 2 mu k mg. On the right hand side, I have 3 ma. So the acceleration will be g into 1 minus 2 mu k by 3. This is what you have?
Yeah.
Okay, very nice. But we'll have to discuss one important what do you say, important idea here. See, there are two possibilities for A, right? Either it will go down or it will stay at rest. Okay, it cannot magically go up. You understand?
Yeah.
So now either the acceleration of A is 0 or greater than 0.
Yes.
Okay,
yes.
So now if you want acceleration to be positive, when A, if you want it to go down, acceleration should be greater than 0. So that means from the right hand side, g by 3 is a constant. So I can say that 1 minus 2 mu k is greater than 0. So mu k should be smaller than half or 0.5. Okay, so if the friction coefficient is greater than 0.5, what will happen? What will be the acceleration of A in that case? It will be, what will be the acceleration of A in case the friction coefficient is greater than 0.5? What would happen? Abhiram, you understand the question?
Then if the friction force is greater than the downward force, it will become negative then, right?
So, but negative means, is that
it's not possible.
It's not possible. So that means what is the physics?
It has to go down.
It has to go down, or the other possibility is it has to stay at rest.
Yeah.
Okay. So this is one thing that we can look at. Now, once we have this, assuming that A is going down, we can substitute in the, let's say, first equation to get T1. So I have mg minus T1 is equal to mg by 3 into 1 minus 2 mu k.
Okay.
So yeah, so from here, I think T1 would be, if I take mg, I think common, I have 1 minus 1 by 3 here. So that's 2 by 3. I think simply plus 2 by 3. So maybe I can take 2 by 3 outside, and I can write this as 1 plus mu k. So did you have this answer for T1? Abhiram?
Yes. Yes.
Okay. So similarly, I can get it T2 from here.
Yeah.
So T2 is mu k mg.
Yes. Can you?
Yeah, I can
hear me?
Yes, I can hear you. I
Yes,
lost.
I got all of that for T1.
Okay. I think then your T2 will also be correct. So we can stop here basically. Okay. So, all right. What do you think? I think it's good time to stop.
Yeah, I think it's, yeah. I'll work on my free body diagrams for like the more complex problems. I think that's why. I think if I have the free body diagrams correct, I'm getting them correct. But okay.
So that's what I said. They're very, very important, and they're not free. So you have to get them. You have to draw them on your own.
Yeah.
Okay. Okay, so I think you try to work on problems. Don't stress too much about the test, because it's after all like something that is going to give you an opportunity to figure out like how best you can prepare. Okay. All right.
Okay. Yeah. Okay. So